Hello everyone. Here we will discuss Bayesian deep learning, which is a relatively new and promising horizon in the field of deep learning. Here with you presenting Shumankar Karmakar and Masum Rahman. I am Shumankar Karmakar and I will present the first part and Masum will continue the rest. So let's start. Bayesian deep learning, such a deep learning network which leads not to be uncertain with your uncertainty. But listening that, you might be wondering, how is that even possible? We'll look further into that now. First of all, let's discuss why we need to be so sure of our uncertainty in machine learning or data science fields. For that, first consider a case where we solve a usual data science problem using traditional and Bayesian deep learning. Consider we trained a dog and cat classifier model using traditional deep learning. It can accurately predict a dog or a cat given an image. But what happens when we feed the model with an input image that is out of the domain, let's say an image of a tiger? Now the model will either predict dog or cat. We know that's just an invalid random output, but there is no way to know that from the model. Similar is the case with some random input image, which is very concerning for sectors like medical, security, or others. Now, consider the same example with an Bayesian model. If it's fed with a valid instance, it can perform just like a traditional model and also provide us with a lower uncertainty score. But when it's fed with an invalid or random image out of the domain, although it predicts a random output, it provides a high uncertainty score. Now, from that uncertainty score, we can know that it's just a random prediction and the model isn't confident with the prediction at all. So, that's a significant edge Bayesian networks have over traditional networks. Now, before moving onwards, let's have a look into two types of uncertainty we have in data science. One is aleatoric and other is epistemic. Aleatoric is the inherent uncertainty in data which cannot be avoided, while epistemic is the uncertainty of the model that can be reduced with more proper data. Now, we discuss the Bayesian network architecture and the key difference between Bayesian and traditional networks. The single point that separates these two is the weight definition of the model. In traditional learning, weight is defined as a single point value, whereas in Bayesian, every single weight is a probability distribution with its own parameter. Therefore, during activation, unlike the traditional, which multiplies those single point values, Bayesian samples a value from each of the distribution to compute activation. However, activation function may be or not may be same with the traditional depending on the model. Now we'll have a short overview of the computation of these distribution parameters. Here we learn the posterior distribution of weights given the training data and use that to predict the test data. But this posterior probability towards the probability of evidence, which is PT, which is intractable, and that's why we approximate the true distribution with a new distribution with new parameters theta. Then we minimize the Kullback-Leibler divergence between these two distributions. So our minimization target becomes this f d theta. Now the first term is Kullback-Leibler divergence and the second term is the negative log likelihood loss, which depends on data. However, this scale term is still intractable, so we make it tractable by making it a closed form drawing fixed in Monte Carlo samples from the distribution. So after algebraic and other simplifications, we obtain the output probabilities and the aleatoric uncertainty of our model. We can also derive the epistemic uncertainty similarly, but that's not in our best interest right now. Now we come to the most significant portion of any deep learning algorithm, that is backpropagation. Since we are sampling weight from the distribution, the question arises whether backprop would be similar like traditional one or not. The weight, if we look at it, the weight is a sampling or randomized node. So we cannot backpropagate gradients through it. So how do we update those distribution parameters? To overcome this, in the literature, there is a trick called local reparameterization. What it does is that instead of drawing W directly from the distribution, it redefines W as mu plus sigma into epsilon, where sigma is the comes from the distribution which is random. Now, therefore, if we look at the computational graph, we see that weight node converts into a stochastic node, and so we can propagate the gradients through it. Now we look into some other promising aspects of Bayesian deep learning networks. Bayesian provides variance for every single weight. Thus, we can use it to determine which weights and intern layers are insignificant and prune the network to make it simpler. Studies showed that pruning with Bayesian, even with just 10% of the total parameters, can achieve similar performance of traditional models on MNIST dataset. Finally, this pruning facility makes the Bayesian networks more suitable to deploy in devices with lower computational power and configuration. However, training is computationally heavy since we are dealing with parameters of distributions instead of a single point weight value. Now, Mason would continue the rest from here.
As Shubhankar has described different aspects of Bayesian deep learning, now let's see how we have implemented the Bayesian deep learning to our problem. Basically, we are implementing an emergency warning system for cardiovascular patients, and we analyze PPG signal derived from a smartwatch. This is how our system workflow looks like. Our patients will wear smartwatch, which will collect PPG signal and upload to the server, where a machine learning model will be run to analyze the signal. If there is any discrepancy in the signal, then the machine learning model will send it to the corresponding authorities, warning that the patient is undergoing an AF. But the PPG signal suffers from some inherent noises, which is caused by motion artifacts during activities. The left one is the ideal PPG signal, and the right one is the signal hampered by the noise. So how does the state of the art models solve the problem? We take debate as the baseline, which is basically a CNN architecture for predicting AF. To perform better in PPG signal, we have to first label the signals. We can use 3 labels: excellent, poor, and good. In DeepBit, they use traditional deep learning models for labeling quality, but the problem is that automated labeling approach generates some undesirable and imprecise quality labels. As you can see that signals with excellent label doesn't seem to be noise free, whereas signal with poor label seems to be quite good. So the automated labeling approach doesn't quite work here. So that's where our model comes into the picture. We name it Bayesbit. So our model, alongside predicting AF or non-AF, it also tells us how certain it is in this prediction. In case of distorted or poor signal, our model is not that much quite sure, whereas for the excellent one, it is significantly confident. As you can see, these are the 2 examples of poor signals, whereas our model is correctly giving high uncertainty score, and this uncertainty score tells us that these signals should be discarded from the dataset. Whereas you can see that in case of excellent signals, our model gives quite low uncertainty scores. So these uncertainty scores tells us which signals should be discarded and which should go into the model training process. So how good Bayesbit performs? As you can see, the performance comparison of Bayesbit with the state-of-the-art models. Apart from the sensitivity score, Bayesbit gives us much better specificity precision F1 score, so which is a quite significant improvement. So here are quite few references used in our model. So thanks for staying with us.